Alright, so let's look at some examples in the second video on geometric sequences. So 3 quick examples which range in complexity. So number 1, for a geometric sequence 36, 18, 9, etc., the nth term, we don't know which order that is, but nth term is 9 on 16. We've got to find the value of n. So in what spot is 9 on 16? So the general term for a geometric sequence is a times r to the n minus 1. Write that in, where a, the initial term, is 36, and the common ratio is a half, because as you're going, multiplying by a half each time. Use a hint, use fractions for this one, okay, not decimals. So that gives us t sub n equals 36 times a half to the n minus 1. Whoops, let me fix that. Oh no, that's right, to the n minus 1. That's all good. So subbing that in, what else do we know? We know that 9 on 16 is 36 half to the n minus 1. Okay, let's go through and solve that then. So dividing both sides by 36, 9 over 576 is a half to the n minus 1. Continuing up the top here, so let's simplify further. We get dividing through by 9, 1 over 64 is a half to the n minus 1. Now if you know logs, you could use them, or you could be really clever. You could write 1 over 64 as a half to the power something, because this is already on the right hand side 1 half to the power of n minus 1. So think about powers of 2. We've got 2, 4, 8, 16, 32, 64. Alright, so 2 to the power 2, 3, 4, 5, 6. Okay, so half to the power 1/6 is half to the power of n minus 1, and so we equate these indices. Because the bases are the same, we can equate indices, so 6 equals n minus 1, and therefore we have 7 is our answer. Okay, next we've got the third term of a geometric sequence is 10, sixth is 80. Find two things, the common ratio, which is r, and the first term, a. Alright, so we know in general we've got a r to the n minus 1 for a geometric sequence. Alright, we've got the first bit of information, so the third term is 10, so that would mean that t sub 3 is a r to the power 2ir squared, and it's equal to 10, so there's an equation 1 for us. And we've got the next bit of information, the sixth term is a r to the power 5, and that's equal to 80, so we have an equation 2. Okay, so if we were to divide the equation 2 by equation 1, in other words, if we want to find the relationship between ar to the power 5 compared to the relationship ar squared, we need to check the same relationship with the right hand side, so that would be 80 over 10, or 8. Here we can divide top and bottom by a, and we've also got our index laws, r to the 5th divided by r squared is r to the power 3, because we subtract the indices when the bases are the same. So it's our index laws, so that's r cubed equals 8, r equals 2. So we have a common ratio of 2. So we need to find the first term. We can go, one way of doing that, we can go back to one of these two equations and do that. And I'm going to choose equation 1 because it's even simpler. So we have 10 equals a r squared, and r being 2, so a times 4. A would be 10 divided by 4, which is 2.5. Or perhaps more handily, 5 over 2. Last example now. Final example might not seem like a geometric sequence until we dig a bit deeper. So we've actually got a drawn pattern, and we've got equilateral triangles in it. And the first triangle has side lengths of 4. So remember, it's equilateral, so all the sides are the same. And the side length of each successive triangle, so they're the ones that follow, is 1.5 times the side length. So there's our proportions, 1.5. Okay, so that's going up in a common multiple. So we already can see that 1.5 would be the common ratio. So r equals 1.5. I like to write it as a simplified improper fraction with these, but that's from here, 1.5, 3 over 2. Okay, so we've got some information too. We've got the first triangle has side length of 4, so t sub n equals ar to the n minus 1. T1 equals 4 if we're looking just at the side lengths. Alright, if we'll just focus on the side lengths, because if you look at these later parts, they're talking about side length. So the side length of 4, and that equals a. We don't know what a is yet. We've got r, it's 3 over 2 to the n minus 1. Alright, n minus 1 is 1 minus 1, which is 0. But anything to the power 0 is 1, so a equals 4. And you might have been able to see that anyway without doing the calculation, because it did say the first one in the pattern had lengths of 4, and that's the starting value, so perhaps you didn't even need to do that step. So we have a and we have r. We're in good shape then. And what is the side length of the fifth triangle? That's T5, so that's 4 times 3 over 2 to the power 4, 20.25 centimeters. Part B, which triangle has a side length of 45 and 9/16 centimeters? Okay, so the term we want is 45 and 9/16. We already know R, we already know A, so let's work that out. So 45 and 9/16 equals 4 times 3 over 2 to the n minus 1. Working with improper fractions is a bit easier, so it's 729 over 16 equals 4 times 3 over 2 to the n minus 1. Let's divide both sides by 4. So that means if you divide both sides by 4, you times the denominator on the left by 4, and we're getting close. Now, if you know logs, you could probably use logs here, but there's another relationship. If you look at the numerators and the denominators, again, 2 to the power 6, like we saw earlier in the video, is 64, is 3 to the power 6, 729. Let's check that out. Yes, it is. So we have 2 to the power 6 over, or sorry, 3 to the power 6 over 2 to the power 6. And we've got 3 over 2 to the n minus 1. That's using your index laws that you know. and again we can equate the indices on both sides because we have bases that are equal to each other. You can see that. So that means we didn't have to use logs, and that would mean that n minus 1 equals 6 again, n equals 7 again, which is a bit freaky. We've got the same answer for two different questions using a similar method. So that means the seventh triangle, so interpreting your answer, seventh triangle is the one that we're after.